see if we can get focus. There we go. Wait, nope. Okay. All right, so yesterday we talked about a similar situation. We talked about our conservative force. What was our conservative force for this?
Gravity.
It was gravity. What was our what were our two non-conservative forces? Tension and air resistance. Okay? So I have given you a value for your air resistance. I don't know if this would actually be what it is. We just made it up. So, okay? Everybody good? We have the height of our cliff that we're swinging off of. Okay? Do we need a tension force? No. Okay, we do not need a tension force. The reason for that we went over yesterday is because the tension force is perpendicular to our motion. So tension is going to go along the rope this way, and our motion is always going to be perpendicular to the rope. Cool? We are assuming that the rope always stays straight, which is a pretty decent approximation. But you know that if you get to the bottom, right before you let go, or at the top if you're above the branch, you get some weird stuff going on. We're going to ignore that for now. Sound good? Okay. Any questions? No? Okay. We are going to need one more number, and that's going to be the mass of our person. How much is the mass of our person?
5.3 pounds.
It would be better to keep it in SI units since 1,000 kilograms. Okay. 1,000 kilograms is a lot of pounds. So this is yeah. I hope the tree can hold his weight. Generally, the conversion from kilograms to pounds is 1 kilogram is 2.2 pounds. So 2,200 pounds. So yeah. Yeah. Okay. So we've got our 2,200 pound guy jumping off the cliff. He's going to swing down on the rope, and he's going to land in the water. Okay. Are we good? Our equation that we talked about yesterday was our work non-conservative is going to equal our change in gravitational potential energy plus our change in kinetic energy. Okay? So I guess we do need a few other numbers. What other numbers do we need? Actually, one number, because we can probably assume one of them. We need a velocity. Okay, so here, actually, that's what we're going to solve for. Never mind, so we don't need it. Here, we're going to assume that he starts from rest. So his velocity up here, or initial velocity, is 0 meters per second. Good? Any questions? Good? Okay. So, we have a value for our non-conservative work. We can calculate our change in gravitational potential energy, right? Because we know the change here. Yeah? And we can use our change in kinetic energy to find the speed that he's going when he hits the water. Okay? Because that's what we're going to find. Everybody good? Okay. So we're looking for the final down here. This marker keeps like working and then not working. So I can't tell if it's dead or not. All right. So we know our work non-conservative. That's going to be our work from our air resistance. We don't need to know the work from tension because we already talked about that. It's perpendicular, so it doesn't add anything in. Okay? So we know our work non-conservative. We can find our change in gravitational potential energy. That's going to be our mass times acceleration of gravity, so mg, times our change in height, which is going to be our final height minus our initial height. Okay? Just to be clear, which ways do you guys want to be positive and negative?
Up is positive.
Okay, up is positive. Are we calling this the zero of potential energy in the water? Okay, that would make sense. I'm assuming we're going to call this direction positive, probably. That would make the most sense. Okay, so we've got that way positive and this way positive. Okay, now this is where some of the beauty of using this gravitational potential energy and kinetic energy comes in, because we just care about the amount of energy here. Okay, because of that, we're not going to have to worry so much about our negative signs and such. Okay, we're not going to have to worry about what direction he's actually going this entire time. Okay, good? Yeah, because if we were doing this with kinematics, we'd have to be very careful about where he is at each spot, and it would be a much, much more difficult problem. Cool? Okay. All right, so we have our change in height, because that's all that matters for gravitational potential energy. Then we have our kinetic energy, which is 1/2 mv squared. I don't know why I put that in front. We'll put that in front. That makes sense. There we go. Good? Okay. So what we're looking for is our V final here. Oh, the marker's not working at all. There we go. What we're looking for is our V final. We already know our V initial. We know our mass. We know our heights. We know our work non-conservative. Good? Okay, so we're going to move everything that we don't need over to here. We're going to leave our final velocity over there. So we've got, okay, this marker is not working. I'm going to try the green. Okay, so we're going to move this over. We can either write it one of two ways. So we can have minus this, or we can bring the minus sign inside and switch the order of these. Which one would you guys prefer? The first way, just minus that. Okay, and then we can move this over. That's going to be plus 1/2 mv initial squared. Okay. All right. Now, this next question I'm going to ask came up a little bit on your assignment. Is this work positive or negative? It's going to be negative work because it's slowing it down. Okay? So we're going to have a negative sign in front of this when we put it in. Do you mind if I go ahead and divide by the 1/2 m? Yeah? Okay. I don't normally do that with the freshmen because they kind of freak out. All right, notice this time, all the other times we could cancel our mass out. This time we can't because the work non-conservative does not have a mass in it. Good? Okay, now, so all we have to do is square root this, and we've got our answer once we put numbers in. Okay? All right. You guys think you can handle calculating this? Are you awake enough?
I don't have my calculator.
Didn't bring your calculator to physics?
Well, I left it at home.
No. I hope it was useful at home at least.
It was.
You do have a Chromebook, you know.
Yeah, I don't like that calculator as much.
Try the Wolfram Alpha website. It's a great one.
Did they have one? Yeah. Yeah. probably. Oh, yeah, I didn't know that.
Oops.
Sorry.
I think they're this set up, right? We'll see. Anybody have an answer? What might be helpful is to realize that your initial velocity is 0, so this whole term is 0. That might be helpful. Also pay close attention to which of these is 78 and which one is 0. Because that'll help you not get an imaginary number.
The gravity's negative, right? Or is it constant?
Yes. Actually, that'll mess things up. Okay. Because that will give you an imaginary number.
Yeah.
Okay. Let's see. Because what you want to get is this. So you get the 500 minus what you get here. That's what you want to get under here. Because this is slowing you down. So we've got a negative sign error somewhere in here.
I switched the gravity to positive, and then I got a real number.
Yeah. Let's see. Because we're calling this 0. So this should be positive 78 here, and this should be 0. And then this should be negative technically. Anybody see a negative sign that we're missing?
No, the 78 should be negative, right? Since it's minus. Since it's final 0
Yeah.
minus 78.
So it's
So then
negative.
that
negative, so that would cancel out here. And then this is also negative, so we've got 3 negative signs here. Because when you have this positive and this negative, you do get a reasonable answer. I mean, as reasonable as it would be if you had a 1,000 kilogram person swinging from a tree, but you know. There was some weird sign stuff in the textbook. Let me see if that would.
39.1.
I got, but I just switched to negative.
Yeah, I got 39.1 as well. But yeah, there's a negative sign issue somewhere in here. Because this should not give an imaginary number. Thank you. All right, I'll see if I can figure this out. Have a good day, guys.
Yeah.
Yes.
What does that mg represent?
Mass times acceleration of gravity.
Okay. So which makes negative. Right?
Oh, how would the data be?
Yeah, so G should be negative because
Right.
gravity is down. This is negative because we moved it from this side over here. This is negative.
Wait. Well, where's the negative come from? Again?
So here, we've got mg
Right.
here.
Yeah.
So we would have to subtract it to
Oh
move
yeah.
to the
Right.
other
Yeah.
side.
Yeah.
And then here, this comes from the fact that this is above. And so it would be a minus
So
constant.
which makes the negative.
Yeah.
This is what makes imaginary number.
Mhm.